So we've been kind of doing the, sort of one step, at least one kind of line, conversion problems, stoichiometry. One thing we've been ignoring is that things run out in the real world, and you've maybe seen on some of these problems that they tell you that you have excess of one reactant, which is cool. And we'll work with that in lab a little bit starting next week. But in reality, sometimes you don't know what's going to run out first, but you might have more than one reactant, and you might not know which runs out. But whatever runs out first is going to obviously limit how much stuff you make, and that's kind of what this next section is about. And that's called limiting reactants. We'll get to percent yield probably on Monday. We're assuming that 100% of the reactants change into products, but that's not always the case. Theoretically it is, but lots of things can happen. Lots of things can limit how much product you make. The amounts of the stuff that you use, which is what we're going to kind of investigate today. The completeness of the reaction. Some reactions only, because of thermodynamics or whatever else, only get you like 50% of what you think they're going to get you. And then the X factor, which we'll kind of investigate in lab, is what you lose in the process. Okay, if you have terrible technique, or you have sausage fingers, or whatever, you spill, you don't filter properly, lots of things can go wrong. And so that can limit how much stuff you make in the end. And so, like the real world, whatever reactant you have in short supply will eventually limit how much stuff you make. Keep going, next page. Yeah. Okay. Now I mentioned the math, it's not new here, you'll find that it's I'm just saying skip this part, don't even look at it. There's some definitions that we have to talk about, and then we'll kind of do the math. So whatever limits the reaction, we call it the limiting reactant, which I think, you guys said last semester, is that true? Oh, it's the same thing, you're going to love it this semester. It's nothing different. Just gotta do things twice.
We had to do that. Whatever it's called.
Theoretical yield?
Yes.
Yes. Next Monday we will.
Are you kidding me?
And then the one that's left over is called the excess reactant. In this reaction, or this example we never looked at, it's HCl. Who cares? Whatever is left over at the end of the reaction, you don't even need to write this part. You just need to write this last sentence. Whatever is left over at the end of the reaction is your limiting reactant. I'm sorry, the excess reactant. The rest of the definition references the above reaction, which we're not going to look at. So, limiting is what stops the reaction. Once the limiting reactant runs out, then the reaction is over. So if you're going to react, let's say hydrogen and oxygen to make water, and you only have 10 grams of hydrogen, you can have all the oxygen in the world, but once your hydrogen runs out, obviously the reaction stops. And that's kind of the idea of the limiting reactant. And the excess reactant is what's left over. Sometimes when you mix two things together, one of them's going to run out first, you might just have some extra stuff sitting in there. That's why it's important to kind of filter things out. And we'll get to a lab like that next week, like I mentioned. If everything works perfectly, the maximum amount that you guys call the theoretical yield, in theory, that is the absolute maximum amount of product you can make based on your calculations. However, it's never really attained because lots of things can go wrong. So it's really challenging to actually get the theoretical yield. Theoretical yield of reactants are based on the limiting reactant. So the limiting reactant is the one that gives you the theoretical yield. It'll make sense when we look at this in a second. So what you can make in theory is always based off of a linear reactant, because once that runs out, the reaction is over, and you can't make any more stuff. Let's look at this as a sample problem. This is where the calculator and periodic table will become useful. You'll notice off the bat that there's a major difference between this kind of problem and the last kind of problem. What would the major difference be? Read it and then tell me.
Two answers.
Yeah, there's two numbers in here instead of one number, okay? So you have two reactants, you've got two numbers. So essentially, instead of saying, the last kind of problems we were saying, hey, you've got a certain amount of this and you've got all this water in the world, so how, they use the word excess. So how much of one of these two things do you make? Now the question says, instead of having a certain amount of one of these and all of this in the world, you're going to have a certain amount of each of them, and one of them is going to run out first. Your job is to figure out which one, and then that tells you essentially how much stuff you should make. So we've got 225 grams of potassium trichloride and 125 grams of water. So you can write it there. So you can see it's 225 grams of this, 125 grams of this. Eventually, one of them is going to run out first. Now, it's not always the one that's the smaller number, because you're taking into account the mole ratio, and so that can be kind of hard to visualize sometimes. But it's not necessarily the one that's the smaller number, because the mole ratio and molar masses and a lot of things play into that. So don't just say, oh, this one obviously runs out first. That's not necessarily true. So one of these two things is going to run out first. We want to know of phosphoric acid, so we want to know how much of this we make. That's the key one in this particular process. So the way that you do this is since you have two numbers, is you just convert this one to this, and then convert this one to this, and whichever one makes the smaller number is the answer. So let's do that. So again, the math is not new. 225 grams of PCl3 and potassium phosphorus trichloride. And the molar mass of that is, thank you, 137.2 grams of PCl3 in 1 mole. Nothing is different here from yesterday. We just have to do things twice. The mole ratio, unfortunately, is 1 to 1. So that makes, I guess fortunately for you, PCl3 makes 1 mole of phosphoric acid. That's the H3PO4. And then you want to know, you could technically stop there, but most of the questions ask you for grams, so it's, might as well just convert to grams anyway. 1 mole of H3PO4 is equal to, thanks, 82 grams of H3PO4. And so when you take 225 times 1 times 82 divided by 137.2, you get 134.5 grams of H3. So if you use all of this, and we're assuming for this first step that we have plenty of this, then you would make 134.5 grams of water. However, we know that we also only have 125 grams of phosphoric acid. We only have 125 grams of water, so let's see how much we should get from that. And then whichever number is the smaller number, that's the correct answer. So we do the exact same thing with 125 grams of water now. The molar mass of water is 18 grams per mole.
No, I'm good.
You're good? Mole ratio is 3 moles of water to 1 mole of phosphoric acid. And the molar mass of phosphoric acid is still 82 grams. H3 and PO4 and 1 mole. So now you take 125 times 82 divided by 18 divided by 3. And you get 189.8. Wow, that's right. Okay. So we've got lots of numbers up here, and this is just some new definitions we kind of learned. So let's kind of just take a step back and look at what we just did. The smaller of these two numbers is called the theoretical yield. And so if the question says, identify the reactant theoretical yield, here is your theoretical yield right here. The smaller of the two numbers is called the theoretical yield. So you know what it is. We never actually get to 189.8, okay, because because the phosphorus, yes, trichloride, runs out first. And so we never actually get to 189. The reaction stops when you make 134.5. That's the maximum amount you can possibly make. Okay. The one that gives you, the reactant that gives you the smaller number, we call that the limiting reactant. Okay, this is the one that runs out first, so it limits how much you can make. That's how much you can make, maximum. Although you don't tend to get that. And then this reactant doesn't run out, so we say it's what? In excess, it's the excess reactant. We'll have some water left over this reaction. You can go and figure out how much water is left over, but that tends not to be fun, and we probably won't do that as much. What's that? It'd be pointless. Well, some applications it's nice to know, but we don't care. But yeah, there'll be some water left over, and you can actually calculate how many grams of water will be left over, but we're not really ever going to do that. And so this number, we never get to, so it's kind of like dreams of what could have been. Okay. So those are the words you need to know: limiting reactant, theoretical yield, excess reactant. The math is the same, and all we care about is the small number.